are going to go rather quickly today. I found out today that some of the other instructors are halfway through chapter 15, and I was like, what? Okay. But you know what? I appreciate why we're where we are, because a good amount of it is that you all are asking fantastic questions. So please keep doing that. I really appreciate that. Okay? Okay. So the end of last lecture, we did a little demo with glow sticks, and I stuck one of the glow sticks in hot water and another in cold water, and we looked at the amount of light given off on those glow sticks. The one in hot water glowed brighter, the one in cold water didn't glow as much. And what that was trying to demonstrate is how temperature affects the rate of a reaction. So in general, increasing the temperature increases the rate of a reaction. And for a reaction to occur, there's some amount of energy that must be overcome in order to get to products. That term, that energy, we call the activation energy. So we can relate rate to temperature using the Arrhenius equation. Where the rate constant K, this is the same rate constant as before, is proportional to, or is equal to, a frequency factor that we label A times e to the E sub A, that's the E sub A is the activation energy, that's minus E sub A, over R times T. And R is the gas constant, 8.314 joules per mole Kelvin. And T is the temperature given in Kelvin. Activation energy you often will see in kilojoules per mole. But you'll notice that our gas constant is in joules per mole. And so we have to be careful here to make sure that we're getting our units the same. So it's a good idea to maybe switch your activation energy to joules per mole, or adjust the gas constant so that it's in kilojoules per mole Kelvin. Either way. Units have to be the same. Okay? That's something to pay attention to. But the idea of the Arrhenius equation is that it relates temperature and rate. And typically we see that if we increase the temperature, we increase the rate, or the rate constant. Interestingly, a rate tends to double for every 10 degrees Celsius rise in temperature. You don't really need to memorize that, but it's kind of an interesting fact. And why does this happen? So when we increase the temperature that a reaction is taking, in a vessel that a reaction is taking place in, maybe it's in solution, we increase the temperature of that solution, we are increasing the energy in which collisions can occur. So this has to do with collision theory, and I think that this, go back for a second, comes up when you're talking about kinetic molecular theory in the gas chapter, but that's from last semester. So let's sort of look at this collision theory in terms of a reaction. So here we have a reaction in which our reactant, I think this is acrylonitrile. I should have written that down. We have a methane group bonded to a nitrogen, which is triple bonded to a carbon. And the product is just a switching of this arrangement. So then the carbon is bonded to a carbon, then triple bonded to the nitrogen. And we have, this doesn't just go from one to another, we have an intermediate state that we oftentimes call an activated complex or a transition state. Okay, it's the thing that exists between the reactant and the product. Could also be referred to as an intermediate. So thinking about this reaction, if we have, draw a potential energy diagram. So we've got potential energy on Y, we've got reaction progress on X, and we go from reactant to product from left to right. We have to overcome some amount of energy to get to the product, okay? So if you look at this plot, we have our reactant shown here, and up here is our activated complex, our transition state. And you'll notice we have to go uphill in terms of potential energy to get to that activated complex. And so what that means is that this reaction requires energy. Okay, we have to go up the hill. Just like when you walk up a hill, it takes more energy than going down, right? It requires some amount of energy. If we're looking at going simply from the activated complex to the product, only that side of the reaction, so transition state to product, now this is all downhill, okay? And so in that case, we see a release in energy. And just like when we were talking about enthalpy for a solution, forming a solution, we have a difference in energy, delta E, that corresponds with an enthalpy. And in this case, energy is given off once products are formed, okay? If we're looking at the difference between the energy of the products and the reactants. Now there's another thing I want to point out. Let me see my next. Yeah, this will be easier to write on. Let's take a look at this activation energy and the magnitude that's drawn here, okay? This activation energy is drawn as the energy difference between the reactant and the top of the hill, the transition state. If that's the forward reaction, that's the amount of energy that has to be overcome. So for the forward reaction, I'm going to write EA sub forward. You have to go up that hill. As we're going to see in the next chapter, and we've sort of seen this a little bit, reactions don't just go from reactant to product, they start going in reverse as well. So from product to back to reactant. And so with that, we can think about another activation energy from product up to the transition state. So that would be, for the reverse reaction, EA reverse. And in this example, it takes more energy to go from product to transition state than it takes to go from reactant to transition state. Okay. You see how the picture is showing that? Which means once we start forming product, the product doesn't go back to reactant as easily. Okay. We saw what the magnitude of a rate constant, what it means in terms of rate last time. Does a fast rate correspond to a large rate constant or a small rate constant? Large. Yeah. Okay. So how does that relate to activation energy? Okay. Sort of alluded to this here. You think a fast rate corresponds to a large activation energy or a small activation energy? Small. Smaller hill to go up, the reaction occurs more quickly. Okay. That's going to be important when we start thinking about catalysts, which is the very last section of chapter 14. Okay. So I mentioned activation energy for the forward reaction and activation energy for the reverse reaction. And we know that if EA is large, then the rate is slower than a smaller EA. Okay. So looking at this figure and thinking about rate constants, what's going to be true? The forward reaction going to have a greater rate constant than the reverse? Is the reverse going to have a greater than the forward? Thoughts? Yeah. B. So the forward reaction has a greater rate constant than the reverse. You're asking if it's the same. Because I always say when we get to dynamic equilibrium, the rate of the forward and the reverse are equal. And I agree with you. For this problem, we're just looking at, in terms of magnitude, if you start with a reactant and you go to product, or if you start with product and you go to reactant. So it's not the best question. But in any case, so what it's trying to say is that activation energy is related to rate constant. A greater activation energy means a slower rate constant. The forward reaction has a smaller activation energy than the reverse reaction, and so that forward reaction should have a greater rate constant. Okay. Make sense? Okay. So again, we're thinking about collision theory here. So we have to have molecules collide with a certain amount of energy. They have to overcome that activation energy in order to react and form product. And one way in which we can favor a product or get over that activation energy is by increasing the temperature of the reaction. And so again, thinking about collisions, when there are multiple collisions, the rate constant increases, so it goes faster as the temperature increases. And this plot on the left here is showing rate constant versus temperature. And you'll see that as we increase the temperature, the rate constant increases exponentially. That's why there's an E here, right? Again, increasing that temperature can really improve the rate of the reaction. And why is that? So this figure is attempting to show you why that is. So these plots are showing distributions of molecules with a given amount of energy. So our fraction of molecules on Y, kinetic energy on X. The blue curve is showing the fraction of molecules at a lower temperature, and the red at a higher temperature. Again, this is Boltzmann distribution. I think this shows up in 1210. If I'm wrong, I apologize. But let's say there's a certain amount of energy that's required for a reaction to occur. That's our activation energy. If you look at this plot at a given temperature, and then you find the area under that curve, you'll see that those with a higher temperature, there's going to be a larger fraction of molecules at that required activation energy or greater. Okay? So higher temperature, larger fraction of molecules that can collide and react to form product. So again, collision theory. Reactants have to collide with a certain amount of energy. They need to overcome EA. that activation energy, and they also need to collide with proper orientation. Okay? So if a reaction is supposed to happen on one side of a molecule and the other side collides with the other reactant, it doesn't work. Okay? They have to be in the right position. Okay, I'm going to just answer this for you, and we can talk about it if we need to. So it says, in the collision molecule, which factor is most sensitive to changes in temperature? We have fraction of molecules with energy greater than the activation energy. That's that Boltzmann plot we just saw. The frequency of collisions that occur between reactant molecules. Orientation factor, that has to do with the proper orientation of the molecules. Are they colliding in the right spot? Or the magnitude of the activation energy. And the answer here is A. So the B is also important, but A is the one that is most affected by temperature. It's the fraction of molecules with energy greater than activation energy. Okay. Once the frequency of collisions is important too. If you think about a gas at high temperature, moving around more quickly, more likely for collisions to happen. But those collisions have to happen with a certain amount of force, a certain amount of activation energy. I'm going to let you all read this on your own time. Okay. Okay, so all right, so here we've taken the Arrhenius equation and taken the natural log of both sides of the Arrhenius equation, going from this to this. And now we have an equation that's in the form of y equals mx plus b. We saw this for our integrated rate laws. We're going to do that again with the Arrhenius equation. And what this tells us is that if we plot natural log of k on y, and 1 over the temperature on x, then we end up with a plot that has a slope of minus the activation energy over r, the gas constant. Okay. And our intercept is the natural log of A. Okay. This is a useful equation. I think you I might be thinking of a different school. I can't remember if you do this type of reaction or this type of experiment. I don't think you do here, so I apologize. But sometimes this is useful to think about the Arrhenius equation in terms of y equals mx plus b. But we can do one other thing with this and generate what we refer to as the two-point Arrhenius equation. You'll use this a lot in your homework. So the two-point Arrhenius equation allows us to predict the activation energy if we know the rate at two different temperatures. That's experimentally very useful. Or you can predict the rate if you know the activation energy at a given temperature. So without going through and deriving this, basically what we end up with is this equation. Okay, this is the two-point Arrhenius equation. The derivation is sort of loosely in this slide, not specific, not as algebraically defined as maybe some of you would like, but it is technically in there. And so what this allows us to do, like I said, if you know the rate constant at temperature 1 and the rate constant at temperature 2, you know gas constant, you can predict the activation energy. Okay. Okay. You would have to be given the rate constants in order to do that. Yeah. So you're only going to have one unknown in this type of equation. It might be a rate constant, but you know everything else, including the activation energy, or you're solving for the activation energy. worry about units because they're going to divide out anyways. Okay, so this is an example of that type of problem. What time are we at? 2:16. Okay, I'm going to write a couple things here, and then I don't think I actually have the answer in my notes. So we'll make this a video for sure. But let's look at the problem here. This says a reaction is studied at different temperatures and the rate constant K is calculated. And what we find is that the rate increases as the temperature increases, and more specifically, the rate doubles when the temperature is increased from 20 degrees C to 60 degrees C. And what is the energy of activation? Now we don't actually know what the rate is for either one of those temperatures, but we do know that it doubles. And that's really all we need to know. So we could say at T, we're going to call T1 20 degrees Celsius. We're going to call T2 60 degrees Celsius. And at temperature 1, the rate constant, we're going to say 1. And we're not going to worry about units. We don't need. And then rate constant 2 is going to be 2. Okay, we said that the rate doubles when we go from 20 degrees C to 60 degrees C. And so we can say that K2 is twice that of K1. Okay. Again, Arrhenius equation. We're solving for E sub A. Make sure you're using temperature in Kelvin. There's a conversion there. And when you're solving for the activation energy, watch your units, okay? So it's either going to be in kilojoules per mole or joules per mole. I'll make a video and solve for this. For some reason, like I said, I don't have the answer in my notes, which is kind of weird. But yeah, that should give you enough to get started if you wanted to try that on your own. Oh, maybe this is why I don't have it in my notes. Okay, skip that. All right, so take a look at these two plots. This is energy on Y and the progress of reaction on X. We have going from reactant A to product B, so A to B, and it's exothermic. You can see that because the energy of the product is lower than that of the reactant. And we have an endothermic reaction, C going to D. Which one has a larger rate constant, A to B or C to D? A to B, right? So going up this hill is smaller than going up this hill. So the rate constant is going to be larger for A to B. Make sense? Yeah?
So you want smaller activation energy for the larger hill?
Yes. Smaller activation energy is a faster rate, which means larger K. Exactly. Okay. We are cruising, you all. Good job. This slide summarizes what we've seen so far. And I also really like this figure. This is from Compound Interest. They make a lot of really nice chemistry-related graphics. There's this one on making chemical reactions happen faster. It mentions collision theory, looking at the how the concentration of reactants affects the rate, the temperature, catalysts, pressure, surface area, all of the things that we've touched on. It's a nice graphic. Take a look at that when you get a chance. Okay, I'm going to stop here on this set of notes. There is a second set of notes I only posted a couple hours ago on Carmen, 14.6-7, I believe. It is in this week's module under Friday, so if you need to grab those, that's there. Are there any questions on temperature and rates? Okay, let's take a 5